We've talked about addition and scalar multiplication of matrices. And remember, this worked pretty similarly to how addition, subtraction, and scalar multiplication worked for vectors. You just do it in sort of the way that you would hope. Well, just like with vectors, if we ask about multiplying two matrices, we now run into some problems here. Because we can't really just multiply two matrices by multiplying their corresponding entries. I mean, we can try and make some definition like that, but the question is, is that actually something useful or meaningful? And as it turns out, not so much. We really have to define this in a different way. So, in order to define matrix multiplication, I want to come up with some notation here real quick. Right? So, what we'll do for a matrix is I want to make row and column vectors. Okay? So I'm going to call this vector here R1, R2, and so on to Rn, or Rm, sorry. So the vector R1 is the number that's made out of, or the vector that's made out of the numbers in the first row. R2 is the vector that's made out of the numbers in the second row of the matrix, so on. I also want to make columns out of these vectors. Okay? Make vectors out of these columns. So for the first column here, I'm going to call this the vector C1. Second column, call this C2, and C3, and so on. Okay? Now, because we're going to be dealing with a few different matrices here, like for example, this one called A, it could be helpful to, say, put a superscript A on these, just to say that, okay, this refers to row 1 of the matrix A, row 2 of the matrix A, column 1 of the matrix A, and so on. Right? This isn't a notation we'll often use here. Really, once we get the hang of how to do the multiplication, we'll abandon this. Right? So, let's say, now that we have this, how are we going to multiply matrices? Well, let me give you the definition. Okay? So, definition. Okay. So if A is the matrix Aij, right? And this is going to be an m by n matrix. And the next matrix here, B, which is, of course, Ij, is not an m by n matrix, but an n by p matrix. Then the product of these two matrices, the product AB, is the m by p matrix given by the following. Or let's erase given by. It's the m by p matrix AB equals Cij, where, right, we need to figure out how to define Cij. Cij, formally speaking, it's the sum from k equals 1 to n of A, I, K, B, K. Okay? What does this look like written out? Well, it's AI1, B1J plus AI2, B2J plus dot all the way up through AIN, B N. Now, what this actually ends up being here is a dot product of two vectors. Specifically, it's it's the row vector, the ith row of column A, dot product with the jth column of matrix. Okay, so again, if we look back up here, we're going to take the ith row in the matrix A and the jth column from the matrix B, and we're going to basically compute the dot product then. Okay? So, this definition seems a bit intimidating at first. At least it can. And it's understandable. It's kind of big and monstrous. So hopefully we'll do an example here, and hopefully this kind of helps clear this up. So let's get some nice matrices here to use as an example. All right. So remember, actually, before we go on to that, so to multiply A and B, right, the number of columns of A must equal the number of rows of B. Okay? So that's up here. If you look in the definition, right? A is m by n, B is n by p. These two numbers must match, right? If they don't match, there's no way we can get this to work out. One of the two is going to have more than the other, and then it doesn't make sense to do a dot product anymore. Right? Remember, the dot product has to be between two vectors of the size. Okay, so that's very important to sort of look at here. So if these numbers don't match up, then we can't compute the product. So let's do this here. Example, if A is the matrix 1, 4, 2, 2, E is the matrix 2, minus 1, minus 1, 8, and C is the matrix 0, minus 1, 0, 4, 0, 2. Okay. Let's look at some products that make sense and some that don't. All right, so let's ask, well, what about A times B? A times B. Does this make sense? Can we do this product? Well, I think the best way to do this is write the size of these matrices underneath each other. So here, A is a 2 by 2 matrix. B is a 2 by 2 matrix. Right? If you write it out this way, if you look at these two numbers here, in order for the two matrices to be able to be multiplied, these have to be equal. And in fact, they are here, so we can go on. So A is the matrix 1, 4, 2. B is 2 minus. Now, when we're multiplying these two matrices, we really want to think about these in terms of rows and columns. This first matrix, we want to think of in terms of rows. The second matrix, we want to think of in terms of columns. Right? Because this is how we're going to do dot products. So like this one here, this is R1A, R1 or R2A. This here, this is C1B, C2B. Right? And now we're going to compute our matrix product. Remember, the 1 entry here says take the first row and the first column. R1A dot C1B. Okay, here we're in the first row, second column. So we use the first row here and the second column here. R1A, C2B. Right? This is always how we're sort of choosing these things. Wherever we are here, like for the next entry, this one here, this is row 2, column 1 of the output. So we use row 2 of the first matrix, 2A, and column 1 of the second matrix. 1. Right? Can you see that pattern? Over here, this is row 2, column 2. So we use row 2 here, column 2 here. 2A, dot, these are all dot products, C2. Right? And now we just have to multiply these out. So for this first one, we're dotting the first row, first column, so times 2, plus 2 times -1. 1 times 2, plus 2 times -1. And then we're just going to keep repeating this. Right? Row 1, column 2, row 1, column 2, so 1 times -1, plus 2 times 8. And then we just, repeat this until we're done. Row 2, column 1, row 2, column 1, 4 times 2, plus 2 times -1. Okay. And finally, row 2, column 2, 4 times -1, plus 2 times 8. Right. And then now you just simplify this all up. 2 minus 2, 0. -1 plus 16, so 8 minus 2. And this is 16 minus 4. So that would be an example of multiplying A and B. Okay. Let's look at another product here. Let's do C times A. Does C times A make sense? C, the size of this is 2 rows by 3 columns. So this is 2 by 3. A is a 2 by 2. So here, these two numbers are not equal, so this is not defined. Right? So again, those middle two numbers have to match up. But while C times A is not defined, what if we write it in the other direction? What if we write AC? Well, now it's 2 by 2 and a 2 by 3, and these are equal. So we can go forward. We can define this product. Right? So A was 1, 2, 4, 2. 1, 2, 4, 2. Okay. And C is 0, -1, 0. 402. Okay. So, well, what are we doing here? Remember, we want to break these into rows and columns. The first matrix in the product is always broken into rows. So, row, row. Right? The second matrix is always broken into columns. Column. Oh, these bubbles are column, column, column. Right? Now notice even though these matrices are different sizes, the number of the number of numbers in each of these circles I made are the same, right? So we can dot product these vectors, these ones, right? So let's get on to it. Okay. So I'm going to skip writing out like the R1.R2 or R1.C1 kind of stuff. Get right on to this. All right, so here, in the first row of the output, we're always using the first row of the matrix A here. So we're going to do 12.04. So that's going to be 1 times 0 plus 2 times 4. All right, now we go to row 1, column 2. This is 1 times -1 plus 2 times 0. And then row 1, column 3 is row 1, column 3. 0 plus 2. Okay. And now we're in row 2, so we're going to use row 2 of the first matrix for everything. Dot product with all 3 of these. So 4 times 0 plus 2 times 4. 4 times -1 plus 2 times 0. 4 times 0 plus 2 times 2. Right, and now we just simplify them. So this is an 8, 8, -1, 4, 4, a lot of 4. Right, and that will be the product of those two matrices. Right, so hopefully that made sense. This is something that you just have to practice a few times and get used to it. But we'll have plenty of practice going on for this matrix multiplication here. So hopefully that makes sense, and the next one.